Good afternoon, everybody. We finished last time we reviewed single phase circuits. We reviewed the concept of phasor, how you express voltage and current in phasor, how to calculate the impedance, and how to implement Ohm's law using the impedance. Well, we'll start today with reviewing three-phase. I know we had all these topics, but because you are going to do experiment in the lab related to single phase, three-phase, so it's important just to review so you will have idea before you do the experiment. And I think you have already experiment number 1. It's in the Dropbox. You have to look for the pre-lab and you do it before you come to the lab. And you submit it to the Dropbox. It's simple task, not very hard. Because I divided every experiment into 2 parts. So you will have enough time to finish. So maybe you know that why the thought about three-phase systems. Well, obviously that they need to transfer greater power, and to be efficient, they thought about using polyphase, like more than one phase. And there are many possibilities, but I think they agreed upon using three-phase system that we are using right now for one reason. First of all, that the power density will be less when you are using a three-phase than using single phase. That's number 1. And also it will save money, save cost, because the power will be divided over 3 phases. So the size of wires, the voltage drop will decrease accordingly, the cost will be less. So it's more efficient and more economical. Using a 3-phase in a way that each phase is separated by the other one by 120 degrees, it make it balance. So when you add the voltage or current that you are apart by 120 degrees, when you add any vectors, like one an angle 0, one an angle minus 120, one an angle minus 240, when you add them, it will make 0. I will show you why it will make 0. If you have a vector on 0 and another vector shifted by or lagged by 120 degrees and another one 120 degrees, the magnitude of all vectors are equal because you are dealing with balanced voltage. So all voltages are equal. So the magnitude of this vector equal to other vectors. And the phase shift is 120 degrees between each phase. That's a balanced 3-phase. So if you say this is phase A, B, C, and by the way, A, B, C, it means if you are moving in anti-clockwise direction, you move A in anti-clockwise direction, you'll find B comes behind A. When you move B, you'll see phase C coming behind B. So that's, I mean, the sequence that we're dealing, we call it A, B, C sequence. And in power system, this sequence, it's known as a positive sequence. That's the positive sequence. Is it important, the sequence? Yes, very important. When you are dealing with power, if you exchange 2 phases, like if you instead of you having A, B, C, you have A, C, B, that will call it negative sequence. What is the effect? There are many effects of negative sequence. For example, if you have induction machine connected to the ABC and you change the phase, then you'll find the rotation will reverse in the other direction and will produce negative current. So that's the sequence, a positive sequence. That's the normal one that we're using ABC. The sum of balanced system like that equals 0. Well, let's just prove it. First, you add A and B, because I mean, I want to prove, is it A plus B plus C equals 0? Somebody might ask, is it voltage or current? It doesn't matter, voltage or current. Balanced voltages or balanced currents in a three-phase system in positive sequence, the sum should be equal 0. If you add A and B, vectorially, you know, so you get, is it the, and then if you add, this is A plus B, and you add it with C, you find they are equal and then equal 0. So that's how, I mean, we say that the balance is equal 0. So three-phase system, another thing, it's balance. It's balance so the sum is equal 0. When you have machine single phase, you have machine three phase, you'll find that the same power. If you are using a three-phase machine, you'll find smaller size having the same power. So they found it's efficient just using the three-phase system. There are many actually. I can talk the whole day about the advantages of three-phase systems. How you produce three-phase system? We are going to study in this course. I think in the end, the last chapter, synchronous generator, the three-phase generator that's used in power station. Simply, just I don't want to go. I mean, we are going to study in details, but just I want to give you an idea. When you look at the generator that produce three-phase system, and always synchronous type, because in the machine when we study, you have two main machines: induction machine, usually used as a motor, and synchronous machine used as generator. But I mean, you can use both like generators or motors. That's but I mean the advantage for synchronous machine used as generator, and we'll explain why. But now, just want to know how to produce the three-phase system. You have here in the middle the rotor. The rotor is like the rotating part. It's a shaft connected to the prime mover, and the prime mover, it will rotate the shaft of the rotor, and the rotor has a magnet. All right, and this magnet has north and south. So when it rotates, it will produce something called the rotating magnetic field. So it'll be like the magnetic field is rotating inside, and every time the magnetic field intersect inductor, and you have three coils, coil A, B, C. So every time when it rotates, and you know how the voltage is produced, or we call it EMF, in the physical EMF, okay, electromotive force. When there is magnetic field changing and intersect or cut some conductor, it produces voltage. So when it's rotating, it will produce voltage, but because I mean the shift of the time distribute like 120 degrees AC between the green, the red, the blue, it's 120 degree distribute, the distance 120 degree. So will be voltage produced in each coil separated by 120 degrees. That's how we are producing three-phase. Magnetic field rotating, and every time it rotates, it produces magnetic field. But because if it's starting here at the green, so the voltage produced by the green will be an angle 0. Be sine wave angle 0. And then we'll go to the second one, will be 120 degree after that, and then 240 degree, and so on. So that's how you produce the three-phase. And that's, I mean, the three-phase. They are equal in magnitude, but shifted by 120 degree. And that's the way that you express the three-phase. That's the voltage of phase A, all right? That's the maximum voltage, cosine omega t. And the other one will be the same thing, minus 120, minus 240. So that's how we get the three-phase balance system. And that's how you express the voltage in a phasor diagram. That's the phase A, phase B, phase C. 120 degrees, yes?
Is the position of phase B and phase C arbitrary, or could we switch?
If you switch it, you will get the negative sequence. But if you have it in this position, that's the positive sequence I'm talking about. A, B, C, it means A, and then behind AB, behind BC, that's the positive sequence. But if you exchange them, then you have A, C, B, you will have another sequence called the negative sequence. Yeah. So that's why when you look at the phasor representation of the voltage, phase voltage, the first one, the voltage VA, yes, you might see, I mean, you say AA dash. What's AA dash? Well, A is like, I mean, any winding has a beginning and end. So when you have any coil wrapped around any pole like that, so you have beginning and you have end. The beginning is called A, and the end of this coil called A dash. So it's trying to tell you that the voltage between A and A dash across the coil, it's equal to Vm and angle 0. And then the second one will be Vm on angle negative 120. And the last one will be Vm on angle negative 240, or you can say positive 120. Both are the same. And that's the way that you represent it. Here I'm showing you the two sequences I talk about, the positive phase sequence and the negative phase sequence. And you ask the question, you see, now if you move A in this direction, what comes behind A? B. And if you continue moving in the same direction, what comes behind B? C. So that's why you write A, B, C sequence or positive sequence. On the other hand, the negative phase sequence, if you rotate A in this direction, you will find not B, not phase B, phase C. Yes. Oh.
First one, B is actually going counterclockwise.
No, you see, I mean, if you're moving like that, move A in this direction. When A move in anti-clockwise direction, what do you get behind? B.
Yeah, you get B on the label is BCC, and the other one's BBB.
That's AA, that's BB, and that's CC. That's let me make it big. That's BB. Yes.
So there's B, A, C.
No, that's A, B, C. That's A, right? If you move A in anti-clockwise direction, what comes behind A?
B.
That's B. And you continue moving B on the anti-clockwise direction, what you'll get behind? C. That's how you can call the sequence ABC. Yes.
Would it be wrong to do the clockwise direction instead? So it would be like ABC to visualize it that way?
No, that's, I mean, the notation that you are using. If you are moving in this direction, every phase like that, you'll find this one behind. And another thing here, I mean, if you look at phase A, it's in angle 0, right? And angle B, it's lagging. Is lagging means behind A by 120. So that's how we can know the sequence. You see what's behind each phase, what comes after each phase.
Like the second order.
The second order, yeah. So you are always moving in this direction, all right? You're not moving clockwise direction. No, you move the phase anti-clockwise direction and see what comes after that phase. Whatever comes after it, that's the right order, yeah. And then when you go to the negative sequence, it's just agreement. You know, if they agree about moving clockwise direction, they can do that. Yes, they can do that. And then you choose it. It doesn't matter. But I mean, they have to find the reference, agree about the reference and if they flip it, that would be the other sequence, be negative. Yeah. So now if you continue taking the same reference and you're moving phase A, you'll find phase C coming behind. So you'll find, you say A, C, and you continue moving C, you'll find B. So that would be ACB. That would be the negative sequence. So that's both sequences that we have in phase, three-phase system. And as we explained that when it's balanced, so you get the sum is equal to 0. Well, now let's see, I mean, how we can connect the three-phase. You can connect three-phase in different ways. You can connect as a star, sometimes you call it star connection, or Y connection. It's the same thing. You call it star, Y, or Y. That's for one thing. How you do that? That's, I mean, the source. You have like, that's A dash, and that's B dash, and that's C dash. You connect the all end, the end of each coil, you connect them together. The all ends of the coils connect together in one node and call it N, neutral. That's how you do a star. Because I mean, you have, that's like a generator, and the generator, we have 3 coils. And we agree that each coil has like beginning and end. A dash, B dash, C dash. You connect A dash, B dash, C dash together in one common point and call it neutral. And the voltage across each coil, like A dash, now I'm not going to call it A dash, I'm calling it AN. A dash, B dash, C dash, they are a common point called N, neutral. So this one in the middle, neutral, it should look like a star, something called star connection or Y connection, because sometimes you can flip it like that. Look, and you can put the generators here. That's star Y connection. Anyway, in star connection or Y connection, we try to find the relationship between phase quantities and line quantities. for the currents, the phase currents in star connection equal to line currents. Why? Let's say that this will producing current in this direction. That's phase, IN. It's the same, the line current. What does mean line current? The current in the line that connected to the generator from outside. If you put this inside a box, that's your generator, all these wires coming out, we call it lines. And what's inside, call it phase. So the phase current equal line current in star connection. But the voltage difference story. If you go for outside here, outside this this machine with this box, you'll find you have A, B, C. So you can't measure the voltage between line and neutral anymore. Neutral is inside. You don't have access to it when you are outside the box. So all what you can do, you can put voltmeter here and measure the voltage between A and B. What's the voltage between A and B? We call it line voltage. Because you are measuring between line and line. We call it line to line voltage, or simply you can say line voltage. Of course, line voltage will not be equal to phase voltage, because if you look at the voltage between A and B, it's related to both voltage A N and voltage B N. So if you have the phase voltage VAN, VBN, VCN, all are equal magnitude, but shifted 120. If you want to find the phase, the voltage between phase A and phase B, which is the line current, you will say VA minus VB, right? So that's VA, and VB will just flip it. It will be like a negative V. Oops. That's so if you do VB, that's minus VBN. You're equal, all equal VM, the maximum value. And then you add, so that you get this value, which is VAB. That's the line current. But VAN, VBN, they are the phase. What is the angle? The angle, if we have this 120 degree, and this straight line, we'll make 60, and both angles are equal, so that will be 30 degree. If you have 30 degree and you make just simple trigonometry, that's, the magnitude is equal maximum voltage Vm. And this triangle, you have 30 degree, so this one will be equal Vm cosine 30, right? So half of this line is equal Vm cosine 30. Vm times cosine 30, cosine 30 is equal radical 3 over 2. And the same thing here, it equal, so multiply by 2. So what you get? Square root of 3 times V max. So in star connection, the amplitude of the line voltage bigger than the phase by square root of 3. So if you have the phase voltage equal to 110 voltage, you want to find between line and line, so multiply it by square root of 3. Not only that, and shift it. Like, what is the angle between VAN and VEB? VEB is leading VAN by 30 degrees. So if we say VAN, let's assume VAN is equal 110 voltage on angle, let's say 15 degree. I'm not starting from 0. And then I'm asking, what's VAB? The corresponding line to line voltage. I will say I multiply square root of 3 times 110. And I know that VAB leading VAN by 30 degrees, so I say is 15 plus 30. That's VAB. So the magnitude is bigger, and it's leading the phase by 30 degrees. And I might ask, okay, how can I find VBC? Well, since it's balanced, you don't have to do this process again. You say VBC is equal to square root of 3 times 110, but the angle will be different. Why? Because there is shift 120 degrees between each voltage. Let me write this one, square root of 3, 110, and the angle is equal 45 degrees. Now I want to find BBC. So you have to keep in your mind, if that's VEB, so what comes behind VEB? BC. What comes behind BC? CA. Maybe somebody knows, how did he know that? I'm embarrassed to ask. Simple. A, we said the sequence is ABC from the beginning. Write it again. ABC, ABC, write as much as you can. So the first one will be AB. The second one, BC. The third one, CA. Just using the last letter from the first line and then use this, the new one. So you can say it's AB, BC, CA. So that's how I know, I mean, that's if it's AB, what's come behind BC and then CA. And the shift is 120 degrees. So now I know VEB is equal square root of 3, 110, and angle 45 degrees. So to find BBC, I will say the same magnitude, but the angle of BBC is behind VEB by 120 degrees. How I write? So okay, this one is 45 degrees, and this one behind by 120 degrees. I say minus 120. And then just I find. So it will be 110. I take a 3, and the angle is equal to, that's negative. So 5, 7. So the angle will be negative 7. And so on, I can find BCA, the same thing. Everything is just behind by 120 degrees. So it's important just to get one, and you can get the rest. Why? Because it's balanced, three-phase. Yes?
Where did we get 110 volts from BM?
No, it was given.
That was given.
That was given as a phase voltage.
And the phase voltage, the voltage between the source and the node.
Yeah, between the source and the neutral. Yeah. So that's, I mean, how, so the summary, if you have star connection or Y connection, line currents is equal line current is equal phase currents, magnitude and angle, the same. But when you talk about phase, the line phase is bigger, is greater than the phase voltage by square root of 3 and shifted 30 degrees, leading by 30 degrees. So VEB will be leading VAN by 30 degrees. That's, I mean, the conclusion, right? What about if the source is connected as delta? Because you have two connections, star connection, delta connection. Did you study this in circuit 2? Star and delta, right? We had in circuit 2. So it shouldn't be strange, just delta, the connection is different a little bit. You don't connect the all ends, no. The end of the first to the beginning of the second. The end, let me just show you how we do it. I did that before in the lab to connect it, because I mean, you are in this day, everything is connected inside. How did we get VM? The star connection again. What's VM? What is VN called? We don't have VN.
It was the first one. Keep going up.
The first one in
Yeah, it's the right under the phase current equals 1.
there is no VN, it's VAN.
VA.
Ah, VN. VN by itself is not defined. VN is equal 0, the reference. But VN is the phase voltage. We did not calculate, it was given that VAN is equal 110 volt on angle 15 was given. Could be different value and different angle. So they are given, the phase voltage. Okay. So when we go to delta, I remember that in the lab long time ago. If you have A dash, B dash, C dash, if you want to make it star, you connect just like that. That's the star, and make it, call it neutral, and then you get the output from here. That's star connection or Y connection. But now we want to make delta. Delta, you connect the beginning of this one, A dash, by B. The end by the beginning of the second. The end by the beginning. And the end by the beginning. And then these are the how. Maybe it doesn't matter to you now because I mean it's already everything is connected, but believe me, we need it. You know, I used to live in the farm for 10 years, and then I get like induction motor, and then you have to connect sometimes star and delta. You'll find on the plate when you unscrew this on the top, you'll find you have A dash, B dash, C dash. Sometimes you call it R, X, Y. It doesn't matter, but you have the beginning and the end, and then if you understand that, you can change from delta to star by this way. So I like it. I mean, you know it. I know it's in the lab, it's connected inside, but it's important to know how to connect it in this. You'll face it. So that's, I mean, the delta. So they make it in a nice diagram here, like, and it looks like delta here. It's okay. But it's very obvious how they did that. Now, the phase voltage and the line voltage are equal. It's not like the star. Because I mean, look at the phase. This is the phase. That's V, okay? And the same, you can say it's A dash. It's the phase. Because you connect A dash by B, as you know. So A dash, it's the same AB. So the line voltage equal phase voltage in delta. Opposite to the star connection. But the line current, different now. It's not the same as phase. Let's just look at for the current. That's the current IA, the line current. And the line A, because you have three lines, line A, line B, line C. What's IA? Using current Kirchhoff law. IA is coming out here, and this is node A, in ICA and out IEB. So you can write IAB, I'm sorry, IA. Wait, go, yeah. IA equal to ICA minus IAB. That's Kirchhoff current law. I'm just showing you how to find the relationship between line currents and phase current. Maybe you had in circuit 2 that the formula was given to you, but I just want to show you how to do it. So if you have any different situation, you can deal with it. Now we need to find or to know the magnitude and the direction of ICA and IAB. Since it's assumed to be balanced, so the magnitude of ICA equal the magnitude of IAB, I maximum. But the angles, it depends on the sequence. Let's assume we're working with positive sequence. So in positive sequence, you'll see that. That will be IAB, IBC, ICA. Do you agree about the sequence? IAB, BC, okay. Now you look for this formula. IA is equal ICA minus IAB. That's ICA. Minus IAB means that you are going to have IAB in the other direction, minus IAB. And then you add. So you complete the parallelogram here, and then that will be the result. Okay. That will be IA. Again, that's, I mean, you have 120 and the 60, the 30, so we'll get the square root of 3, cosine 30. So this magnitude will be square root 3 times I phase, which is IAB or IC, and the angle will be different here. IAB, it's on angle 0, but IA, it's like ahead by, that's 30, that's 120, it's ahead by 150, leading by 150. That's what they got. So line current in delta is bigger than the phase current by square root of 3 and leading the phase current by 150 degrees. You can have the formula with you in a formula sheet. You don't have to drive every time. That's okay. But you understand how you got it. No, I didn't. I know it's ahead by 30 degrees. I said 150 degrees. That's 120. And that's straight line. So that's 120 up to here. Let me just make it clear here again. If you have three phase, that's a question. I said, how do you know 30? Now I understand the question. That's you have the three phase here, A, B, C. And if you flip this one on the other side, we know that this is 120 degree. So that will be 60 degree. And if you make the parallelogram and since they are equal and then you make the resultant, that will be divided into two equal angles. And that's 60, so that will be 30, that will be 30. That's how I got the 30 here. So the total will be 120 plus 30 will be 150. Okay. So we got the relationship between the okay, good. I mean, I like it. You guys ask about everything, anything just come in mind. So we got the formula here, and then of course we can. I'm not going to waste your time. The same thing you can do it with load. Then you ask me if there is difference between the load and the source. Not big difference. The only difference will happen in the angle. Leading 150, leading 30, and we do it in the star. Might be, I didn't check out, maybe it's the same as the source, but delta, I'm sure it's different. When I did it, I proved it, I found the angles are different, but still the same rule. In delta, the phase of voltage equal the line voltage, and the difference just in the angle. In a star, the voltage phase in the star is smaller than the line voltage. That's by square root of 3. It's the same for both load or source. The only difference you will observe just the angle, how you calculate the angle. What do you mean by that? Means like in delta, we know that the line current is equal √3 the phase current, leading by 150 in the source. But when you have load like that, connecting the load, you'll find that the line current is lagging by 30. Okay. Of course, there's explanation for it. I mean, when you do the same vector direct. Okay. So let's just solve one example. We have source connected as a star, and the phase voltage is equal 110 voltage on angle 0, and then this is phase B by 120, 240 is just normal balance. So that's, I mean, that's the source for the generator. And then that's the load. Also, the load's connected as star. How do I know it's connected as star? Doesn't look like star. No, because I mean, they all connect at one point, the neutral. So I know that's star. So simply you got like a star source, and you got star load, and you connect it by transmission line, and it's a very normal situation. You have generator 3-phase, you have load 3-phase, and you connect the source to the load through transmission line, so you can feed the load. That's a very normal. Yes.
Never mind. The image went off for a second.
Pardon me?
The image went off the screen for a second.
Oh. Okay. So that's a normal situation. So how we can solve something like that? I will tell you about technique that I used to do when I was a student. If you have balance situation, balance load, balance source, everything is balanced, convert the 3-phase to single phase. Balance condition. And we are dealing only with balance condition right now. When we deal with the imbalance, then we can talk about it. I don't like to confuse you two things together at the same time. So convert the 3-phase to single phase to be easy. I got you a very simple situation. Star source or connected star source, and you connect it to load is also star. So we pick one phase from each. So the source is 110, angle 0. I only take phase A. When you take phase A from the source, take phase A from the load. So I will just say I have 110. That's the source. And the angle is 0. All right, so we have to be careful about the angle too. So 110 and angle 0. That's the voltage from A to N. Let's agree about something. When you are dealing with source, use small letters, the lowercase. When you are using the load, use capital letters, just to distinguish between both. And we got a load here, phase A. We agree that will be A, capital, N, capital, N, small. And the load is equal 10 plus J8. All of them are equal. That's how we know it's a balanced load. So you just write the impedance 10 plus J8. And that's ZL. And that's B source, AN. And then connected by transmission line has impedance too. The impedance is given 5 minus J2. All of them, they are equal. 5 minus J2. And the current will flow in this direction. You can call it anything. I will call it IA. So now it's easy to solve. Just very simple circuit. Everything is easy. What was the question here? Calculate the line currents. All right. To do the line current, it's just IA. It's line current already. So you find the total impedance. You divide the voltage by the total impedance to get the current. It's done. So IA will be equal to the voltage VAN divided by the transmission line plus the impedance of the load, and all bare phase. The voltage is equal 110 on angle 0. Transmission line is equal 5 minus J2 plus 10 plus J8. So B 110 angle 0. 5 and 10 is equal 15 minus J2 and B plus J6. And just use your calculator, the complex. You should know how to use your calculator complex now, because you will not have time in the exam just to do it by your hand, or use MATLAB. I wonder if you have MATLAB here. Oh, you don't have it. You have a calculator you can use, and I did already. And I found that IA 6.81. So IA is equal to 6.81, and the angle is equal to 21.8 degree. And you are not done. You don't just did one phase. You got to find IB and IC. So how can you find IB? IB will be, since it's balanced, will be the same magnitude, just to be shifting the angle. So it will be 6.81, and the angle here 21.8 minus 120 degree. That will be that will be 6.81, and the angle will be negative 1. I'm sorry, this is negative. If yes, that's negative. Yeah. So it'll be negative 141.8. You want to find IC. I see you have two choices. You can subtract 120 from IB, or you add 120, because I mean, when you look at the angle here, that's, I mean, minus 120, minus 240, or you can plus 120. So you have the two choices. Let me continue and make it the same thing. I will subtract each phase from another by 120, just to be systematic. So we'll have 6.81, and I get the last angle I got, which is minus 141.8, and I subtract another 120. So I will get 6.81 negative 261.8 degree. When you have big negative number like that, big negative angle, even when I get the equivalent positive, all what you're supposed to do, you add 360 degrees. That's all, to be equivalent. So I will just write here in clear to understand how I got it. 6.81, and it's the same, negative 261.8 plus 360. And we'll get 6.81, and the angle is equal to 98.2 degree. Because they don't like to have negative number, negative angle more than negative 120. Don't make it more than that. Just the idea about it. So be readable and easy. Okay, so that's, I mean, how you solve the three phase. Let me give you a quick quiz, 5 minutes. Simple one. And then we'll be done with the lecture. Go ahead, 5 minutes. And then whoever online, send me in 5 minutes. Yeah, 5 minutes. No calculation, nothing. Just, I mean, if you understand what we did. For me? Okay, just let me know. 5 minutes. Okay. Is it clear? Can you make it bigger? Okay. Yes.
Would this be a positive sequence? Like
Positive sequence, yes, yes. Any problem that you solve, it's assumed to be a positive sequence, except if something else is mentioned. Yes.
yes. All the sequences.
You have to remember the sequence. That's VAN, and that's VBN, and that's VCN. That's the phase. When you make the line, what you'll get? You'll get VEB, right? VC, VCA. So everyone has relationship. There is a relationship between VAN and VEB that I proved. Accordingly, will be relation between VBN and VBC, VCN and VCA. Every just couple like that. So you look what you have. That's VCN. When you say VC, it means VCN, right? So you are here, giving the angle, and that's VCA. So the same shift between VAN that will prove it and VEB, it will be the same shift for each phase. For example, if we say the shift is 50 degree, for example, so it'll be 50 degree for each phase on line because it's balanced. So that's how, I mean, you get it. Just to, of course, you know the relationship with the magnitude. I'm sure that you know the magnitude, but just you're looking for the angle now.
VC is the same as VCN.
Not the same, would be related to, like VEB related to VN.
Okay.
What's the relationship? I proved it in the lecture. The relationship between VEB and VN. So the same relation, you got it? It's just the angle is different. The VN was in 0, maybe different angle, you know. Even I give you example if I don't want to flip the page, but I give example if it was in 15 degree, what you do. If you go back to the example that I saw, it will be very similar. Let me just go back to the lecture and the example when I showed the Y. This is the Y. And that's the relationship that I proved. That's the line voltage between AB and BC and CA and so on, between each one. But you have to remember that was given like, that's an angle 0. When this was angle 0, that's 130. When this negative 120, you'll find this minus 90. Okay. So it's like, I mean, the relationship, even you don't have to confuse yourself, just that's an angle 0, that's negative 120, negative 240. Now CN is not given, is not negative 240, it's different angle. So see the difference and just adjust to it. For me? I have to go back to the question, see what to answer you right. Yeah, find line to line voltage VBC. The required find VBC only.
Right, like 120 or VN. Because it was like VN in there in those equations.
VM is the maximum voltage, the magnitude.
Okay.
Yeah. So the magnitude here is 120. I can tell you this is VM because this is the phase. Yeah. I'm not going to say what. Another way to look at it, that you have VC, find VB. Because you want to find VB. What's VB? Can you find VB if you know VC is known?
Would VB the same thing as VBC?
No. But I'm saying, I mean, if you have VC and you know the sequence ABC, can you get VB? Of course you can get VB. You can get the VB angle and magnitude? Yes. If you have VB and you have VC, you subtract and get it by Victorial, and you get it. You don't have even to memorize any law. Just do it. Find VB first, then subtract. Subtract by Victorial just by sketching as I did as a vectors. Of course, the magnitude of VB is equal to VC. The only difference is the angle. Is VB leading or lagging VC? VB is leading. By how many degrees? 120. It's balanced. So what are you supposed to do? You add 120 to the angle that you have. Then you got VB. And when you subtract, you get VBC. It's just simple as this. Because VBC equal VB minus VC. Yeah, I'll give you one more minute, not to make you late. If you are done, you can give me the.
I will post the answer on the Maybe it's like
Thank you.